All right, this presentation is on chapter 19, which is thermodynamic review. We can start it off with the artwork of my daughter. She wanted to give you guys something to enjoy. So it says, "Hi, my name is Stan. I hope you have an amazing day and enjoy class. Mr. Luck is a great teacher, but not as great as me. I mean, meow." So there you go. There's Stan. So, sorry, Stan. Gotta go. Like your tie, though, and your lab coat. So chapter 19 is thermodynamics. So remember, the first law of thermodynamics is that energy is conserved in any reaction, right? So we looked at that when we did thermochemistry early on, chapter 5. So now we're into thermodynamics, and we get to the second law of thermodynamics, which is that entropy is not conserved in a chemical reaction. In fact, we know that the entropy of the universe always has to increase. So what's entropy? So entropy is randomness. Entropy is freedom of motion. Entropy is the ability to move without constraint, to fill large volumes of space, to spread out undeterred, to be able to mix and move, right? So all of those things are ways that we can visualize and think about entropy. So when we talk about freedom of motion, we can start talking about what are called microstates. Microstates would be how many different ways can that object exist in some volume of space, let's say. So we have positional entropy, which is, well, it could exist in any spot in that area or in that volume. We can talk about entropy of motion, like how fast is it moving, which direction is it moving. All of those things go into what we consider the microstates. And we know that the number of microstates is determined by the Boltzmann equation, right? So now we have this connection between more entropy means more microstates. So the Boltzmann equation is the S, which is our entropy, equals K natural log of W, where W is all of the possible microstates that something can have. And your K is the Boltzmann constant. That's not related to the equilibrium constant. It's just a Boltzmann constant. So we have this equation that he used, which gave us a mathematical method. And this W was related to Boltzmann's distribution of particles based on energies and all of that, which we have also used for looking at energies of particles when we're talking about evaporation and activation energy and all those sorts of things. It all ties into that same calculation that Boltzmann did that gives us that range of particles and how they can behave. So now we have this concept of what entropy is. So we start thinking about situations where our entropy might change. So anytime we have a phase change, we're going to have huge changes in entropy. When we start with a solid, that's our lowest entropy. So the third law of thermodynamics is that the entropy of a system at 0 Kelvin is 0. That's the only time you don't have any entropy. And the reason is because the particles aren't moving, and you can compress them into a space. Now, if it's under pressure, we'll compress it into a space where all the particles will just line up until it can't be compressed anymore, and they can't move, and they're stuck in place, and that is when, and the only time, that your entropy is 0. So anytime you raise temperature, your entropy is going to increase also, because you're giving them more freedom of motion, you're giving them more possible energies that they can have of how fast they move. So that's the first part. But the second part then with the phase change is also allowing them to move past each other, allowing them to spread out, allowing them to move more randomly. All of those things are going to be increases in entropy. So obviously if a solid dissolves, that's going to be an increase in entropy when it becomes ions or particles that are floating around now in the solution rather than being stuck in one spot. And obviously if a solid melts into a liquid, that's going to give it more entropy because now it can move more freely and it can spread and it can, be affected by gravity now and roll off a table and all those things it couldn't do anymore when it was a solid. And when a liquid turns into a gas, it's going to be a huge increase in entropy because now you have complete freedom of motion. The particles can go anywhere because they're no longer bound to each other. So you have these huge changes in entropy at phase changes, but you also have a constant change of entropy based on temperature. Your temperature goes up, your entropy goes up. As your phase change happens and there's more freedom of motion, then your entropy increases drastically. So oftentimes, like if you're looking at water and you're looking at your entropy, you know, and we talk about 0 degrees Celsius and 100 degrees Celsius. So you're starting with water at some temperature below that is ice. So you're going to have an increase here. And then at the phase change, you're going to have a huge increase. And then you're going to have an increase as the temperature is going up. And at the phase change, you're going to have a huge increase in entropy, right? So there's your phase changes where the entropy is almost vertical change. And then you also have the slope where your temperature is increasing, right? So all of those things are going to factor into our entropy and how our particles move. So what we end up with is we end up with the delta S of the universe is equal to the delta S of the surroundings plus the delta S of the system. All right, so we have this equation talking about the second law of thermodynamics saying this always has to be a positive. And if the delta S of the universe always has to be a positive, then that means the sum of these two things also has to be a positive. Well, your system and your surroundings are doing different things as a chemical reaction occurs. So if the entropy of your system goes up, meaning your substance turns into a gas, how is that going to affect the surroundings? Will it lower the entropy of the surroundings by having these extra gas particles in there taking up space? Is it going to cause the entropy of the surroundings to increase now because maybe the surroundings didn't have maybe the surroundings didn't have much energy in it, and therefore the addition of the gas adding that energy to it also caused that to go up. So obviously, if both of these things are positive, then the delta S of the universe is going to be a positive. All right, so what does that mean? Well, the delta S of the universe being positive means that that reaction is going to happen, and it's going to happen all the time. So this is one indication that our reaction is spontaneous, meaning it's going to occur. What if our system is increasing in entropy, but when it does that, it causes the surroundings to have its entropy go down? Maybe now by putting this gas that was created into the volume above where the gas was being created, now it causes more particles to be in there, which is going to lower the microstates and the possible places that those particles can occupy. So it lowers that. Well, now the delta S of the universe may not always be positive. It's only going to be positive if the system entropy change is bigger than the surroundings. Okay? And if that's the case, then this will be a positive, but only if this is bigger than that. What if this is bigger than that? Well, that means that, sorry, that's not what I want to say. If this was bigger than that, then this would be negative, and therefore that reaction would not occur without outside influence, which that outside influence is something external making that reaction occur, and somewhere using that external energy to make that reaction occur will cause the universe to have an increase in entropy. But you have to bring something else in to make it occur if this ends up being a negative. So what if the surroundings is positive and the system is negative? Then again, we run into the same situation where the surroundings has to be a greater entropy increase than the system in order to make this work. And then you could have the situation where both of them have a decrease in entropy, and then that's going to be negative all the time, which means that that reaction is never going to occur unless you put some outside influence into it to make it occur. All right, so taking it to the next level, because we don't usually look at it in this situation, what we find is that the surroundings and the system are two separate places that we're looking at. And so the delta S of the system, if we start to focus on that, then we want to focus on the delta S of the surroundings and how it relates to the system. Well, how can we tell what the surroundings does? Well, the way we can tell what the surroundings do is we start to look at the delta H of the system. So whatever the delta H of the system is, if we reverse that, then that becomes the delta H of the surroundings, right? Negative the delta H of the system will end up being the delta H of the surroundings. All right, and what we find is that if we have that delta H of the system and we divide it by temperature, then that is equal to the delta S of the surroundings. So we can go substitute that in down here and say, well, the delta S of the surroundings is actually equal to negative the delta H of the system over temperature, right? Because if that temperature hardly changes, then we said that the entropy's hardly going to change. So this is all related in a isothermal system, is that your delta H of the system divided by the temperature is going to give you the delta S of the surroundings if this temperature change is very, very small. All right, so now we have this equation, and so now we can go and multiply everything times minus T. So if we do that, we get minus T delta S of the universe equals delta H of the system minus T delta S of the system. And when we have negative T delta S of the universe, that's equal to our delta G. And so we get our delta G is equal to our delta H minus T delta S. So this now gives us our equation that we can use where we can get the enthalpy and entropy of the system to be related to the delta G, which is our free energy of the system. So our free energy is the total amount of energy of both the enthalpy and the entropy, or the entropy of the system and the entropy of the surroundings, that is released into the universe. All right, so that's why they call it free energy, because it's all the energy now that's been freed up to go off and do whatever it needs to do or whatever it can be used for. All right, and that's the 100% efficiency that we would get out of some sort of reaction. If we release all this energy and can collect it all, then we have 100% efficiency. All right, so what does that mean about this? Well, it means that we want our delta G, since it's minus T delta S, we want our delta G to be negative in order for our delta S to be positive of the universe. So we want our delta G to be negative. So what ways can we get our delta G to be negative? Well, the first way is if our delta H is negative, which means our reaction is exothermic, and our delta S is positive, because if this is positive, then T times that is also going to be positive, since temperature is always in Kelvin. And so negative, all that positive, is going to make it a really big negative. So if our entropy is positive and our enthalpy is negative, it's exothermic, but we're creating a gas, let's say, then that's always going to make for a spontaneous reaction. If our delta H is negative and our delta S is negative, then this will be negative, but only when this negative part over here, when it gets multiplied out, is smaller than that one. So this is going to be negative then only at low temperature, because the smaller the temperature is here, the less this has an effect on your free energy change. If the temperature is, let's say, 1 Kelvin, and the delta S is something in joules, then this negative joules is not going to become positive enough when you do the math to make it more than the negative in kilojoules here. So if your temperature is small, then it doesn't matter that your entropy is negative, because your enthalpy is going to override. If this is positive and this is positive, then this will be spontaneous at high temperature, because now you need this to be bigger as a positive, so that when you do the math, it becomes a bigger negative, then that is positive. So the bigger the temperature here, the more this positive becomes negative when you do the math, and therefore it can override the enthalpy. Right? Because remember, when I say do the math, it's, negative that big positive value that's in here. And then the last possibility is where this is positive and that's negative, and that's never going to be spontaneous. There's nothing you can do. There's no temperature or whatever that you can do. So that's the same situation as we said earlier, where our entropy change of our system is negative and our entropy change of our surroundings is negative, and therefore the entropy change of the universe is also going to be negative, which means we're going to have to do it with some outside influence. So there's no situation where an endothermic reaction with a decrease in entropy will ever be a spontaneous reaction. Okay, so examples of the top one would be a combustion, right? Negative enthalpy, positive entropy, because you're producing gases from whatever you're burning, and it's usually more moles of gas than you're starting with. So that's always spontaneous. That's why once the reaction starts, it never stops. Where you have an endothermic reaction with a negative change in enthalpy would be, let's say, the recrystallization of recrystallization of like sodium acetate. When that comes out of solution and recrystallizes, it's an exothermic process. It's what they use in hand warmers. So you're going to have a solid forming, which is going to be a negative entropy, but it's exothermic. It's releasing energy to you, and it's releasing more energy than the entropy change, and so it's still going to be spontaneous. And the third example would be one where the acid with baking soda is an endothermic process, but because you release the carbon dioxide gas, your entropy change is so huge that you still end up with a negative free energy. All right, so there's your understanding of that equation. So how do you figure out these values? Well, you can figure out the values lots of different ways. Obviously, they can give you those values in a table. But the other options you have is to remember that all of these things are state functions. And so when you use that table, you could always do delta G equals the sum of the standard free energies of formation of the products minus the free energy formation of the reactants. Or you could do it with the entropy too. Equals the sum of the standard entropy of the products minus the standard entropy of the reactants. So you can do any of those things along with the delta H, which you already knew how to do in chapter 5. So, you can use any of these to find that. Sometimes, though, they won't use this one, because of conditionally, those numbers in the back of the book might not always be perfect for that, but you can use it to find the enthalpy and the entropy, and then you can use that to find the delta G from there. The one thing you want to watch out for is your units. Entropy is in joules per mole Kelvin, while your enthalpy change is usually in kilojoules per mole. So watch that your units here are different so that you don't make a unit mistake when you're doing the problems. That's one of the most common things that people end up doing. So there you have that. So how can you use this to find, let's say, a normal boiling point or a normal melting point? Well, the answer is that if you know the phase change point, then that means your delta G is 0. Right? Because if you're at a phase change, you're at equilibrium. So if delta G is 0, then you can do delta H equals T delta S, and that will give you your give you a way to solve for your phase change temperature. All right, they would have to give you a way to get the enthalpy and entropy at that phase change so that you could figure out what the temperature is from that. But that's how that works, because delta G is 0, so you can bring the T delta S to the other side, and you get those two things equal to each other. All right, well, how does this relate then to equilibrium? So what you end up with is that your delta G, under any conditions, is equal to your standard delta G at 298 Kelvin plus RT ln Q. But at equilibrium, your delta G is 0. So that means that delta G0 is equal to, if I bring the RT ln Q over to the other side, negative RT ln, but now I'm saying I'm at equilibrium. So since that became 0, then ln Q becomes ln K, and that's where that equation comes from. All right, where you get that delta G equals minus RT ln K, and this is the K from the equilibrium that you can use. So that then ties in with all of the other equilibrium situations that we can have where you might need that K. And it also helps you understand what it means to be at equilibrium. You are at equilibrium when you are at the lowest value for delta G that you can be at, meaning that you've released as much energy from the system as you can. So graphically, what we're looking at is our equilibrium is where we're at the lowest point of this graph. And if you go any way in either direction, your delta G is going to start to be higher. All right, so this is your lowest value for G here. And so this is where your Q is greater than K. So that means that your reaction is going to have to go in reverse to get back to K, and this is where your Q is less than K, so your reaction is going to have to go forward in order to get to your equilibrium, and in the case of doing both of these things, your delta G will be negative. But when you're at equilibrium to go in either direction, your delta G now will end up being positive, so you're going to need to add energy to the system to get it out of equilibrium. And that's why when we talk about equilibrium and all the other things we do to the system, it's always external things, changing the volume. Something else has to put pressure on it to change the volume, to change the pressure in the system. Something else has to inject particles into it in order to change concentrations. Something else has to heat it from the outside to change the temperature, because we have to do those things to pull it out of equilibrium. And then what's in the system will automatically, according to the laws of thermodynamics, work its way back to equilibrium again. So that's how Le Chatelier relates to all of this as well. So there's a pretty good overview of everything that's in Chapter 19 that you would need to know about thermodynamics.